Вроде поехали. Как там со звуком? Раз, раз, раз. Есть? Ну, хорошо. Well, okay, so in the previous lecture we discussed the Gelfand-Dynamic theorem for commutative C-star algebras, which states that you have a commutative unital C-star algebra, A, then the Gelfand transform, which acts from A to the algebra of continuous functions on the maximal spectrum. So the Gelfand transform is an isometric star isomorphism for any commutative unital C-star algebra. So in particular, we see that any commutative unital C-star algebra is isomorphic to the algebra of continuous functions of the compact Hausdorff topological space X, which is necessarily homomorphic to the maximal spectrum. By the way, a little remark concerning this result. So what if we take a non-compact topological space X, an arbitrary topological space? Well, in this case, of course, the algebra of continuous functions is not a C-star algebra, because there can be unbounded continuous functions, and we cannot define the supremum norm. However, we can consider the algebra of bounded continuous functions, CB of X. And this is actually a commutative unital C-star algebra for any topological space X. So according to the Gelfand-Dynamic theorem, it is isomorphic to the algebra of continuous functions on a compact Hausdorff topological space, that is, on the maximal spectrum of this algebra. So what is this space? Actually, it turns out that the maximal spectrum of this algebra has a very classical topological meaning. This is exactly the so-called Stone-Čech compactification, beta x of X. So this is what we get after we apply the Gelfand-Dynamic theorem to the algebra CB of X. And actually, this is probably the most convenient way to introduce the Stone-Čech compactification. Okay, so this was a little remark. And today our first goal will be to apply the Gelfand-Dynamic theorem to constructing the continuous functional calculus in C-star algebras. So suppose we have a Banach star algebra, A, unital Banach star algebra, and a normal element little a of A. So roughly what we are going to do is to give a precise meaning to the expression f of A, where f is a continuous function defined on a suitable subset of the complex plane. What f of A is, in case where f is the exponential function. We can just write the usual power series for the exponent and then substitute A into this series. And in fact, the same procedure works for any holomorphic function on the complex plane. So what we want to do is to extend this expression to the case where f is an arbitrary continuous function, and so it is not necessarily given by a power series. So let's now give some definitions. Suppose that K is a compact subset of the complex plane, and let little t denote the inclusion map of K into the complex plane. T of lambda is lambda for any lambda. And we give the following definition. A continuous functional calculus a continuous functional calculus for our element little a on K, on this compact set K, is a continuous unital star homomorphism gamma A from C of K, from the algebra of continuous functions on K, to A, such that this homomorphism gamma takes this function t, the coordinate on K, to A. So this is the verbal definition. By the way, a little remark concerning the terminology. The word continuous here in this notion refers not to the continuity of gamma itself, but rather to the fact that gamma is defined on the algebra of continuous functions. So, for example, if we replace here C of K by the algebra of holomorphic functions on a suitable open set, then we'll speak about holomorphic functional calculus. So the word continuous here means that we want to apply continuous functions to our element. Okay, first of all, let's observe that if such a calculus exists, then it is unique. If gamma A exists, then it is unique. Well, actually, this is a simple application of the Stone-Weierstrass theorem. Because if we look at the subalgebra of C of K, generated by the identity function t and t bar, the complex conjugate of t. So this is the algebra actually of polynomials in t and t bar. Then this subalgebra is dense in C of K, just because it is a unital star subalgebra which separates the points. So it is dense in C of K, but on the other hand, we obviously see that gamma is uniquely determined on this subalgebra. So it takes 1 to the identity of A, t to the A, and t bar to A star, because it is a star homomorphism. And that's it. So we see that gamma is uniquely determined by this equation, by the property that it takes t to A. Okay, so if it exists, then it is unique. Now, how about the existence? Well, let's first of all observe that we have an obvious necessary condition. If gamma exists, then the spectrum of A is contained in K. So this is the condition on our compact set K. K should contain the spectrum of A. Well, indeed, if it exists, then we can look at the following picture. So the spectrum of A, so what is A? A is gamma of t. A is gamma of t. And gamma is a unital homomorphism from this algebra to this algebra. And we know that each unital homomorphism reduces the spectrum. So this is contained in the spectrum of t in the algebra of continuous functions on K, just because gamma is a unital homomorphism. But the spectrum of a continuous function is just the range of this function. And the range of little t is just K. And we get that the spectrum of A is contained in K. So this is a necessary condition for the existence of our functional calculus. In the general case, I don't claim that it is sufficient. In fact, I recommend you the following exercise. Construct a unital Banach-Starr algebra A and a normal element little a, such that gamma never exists, such that gamma A never exists, whatever the compact, whatever k is. So for any k, we have no gamma. Fortunately, if A is a C-star algebra, then everything is okay, and what we're going to do is to show that this necessary condition is also sufficient for the existence of the functional calculus. Before we prove this result, let's introduce some notation. Suppose that A is a C-star algebra, and S is an arbitrary subset of A. We define the C-star subalgebra of A generated by S to be the intersection of all C-star subalgebras containing S. And we denote this subalgebra like this. So we consider all C-star subalgebras containing S and just take the intersection. And clearly this is indeed a C-star subalgebra, and it has the property that this is the smallest C-star subalgebra containing S. This explains why it is generated by S. In fact, we can easily describe this subalgebra a little bit more explicitly. So let's observe that the C-star subalgebra of A generated by S is the closure of the linear span of all finite products A1 to AN, where the letters A1 and AN belong to either to S or to S star. And N runs over the natural numbers. So we consider all words in this alphabet S and S star and take the closure of the linear span. Obviously this is a C-star subalgebra, and it is the smallest C-star subalgebra containing S. Here's a useful special case. Suppose that A is unital and little a is a normal element of A. Then let's look at the C-star subalgebra of A generated by little a and the identity. And let's observe that this subalgebra consists, it is actually the closure of all polynomials into variables applied to A and A star. So here P runs over the algebra of polynomials in two variables. So we consider all such elements, and then we take the closure in A. In fact, this is a special case of observation 1, because if, well, A is normal, so when we consider all such words, so each AI is either A or A star. So this will be just a monomial in A and A star. And we get this. And even more special case is the case where A is self-adjoint. Oh, I said that A is normal, but I forgot to write this explicitly. Little a is normal. So since it is normal, each such word is just a monomial in A and A star. And if, in particular, if little a is self-adjoint, then we can take polynomials in one variable and we get the same result. This is just the closure of all polynomials P applied to A. Okay, so let's now come back to the functional calculus. We have the following theorem. Suppose that A is a unital C-star algebra. Little a is a normal element of A. Then, for each compact subset K of the complex plane, which contains the spectrum of A, there exists a unique continuous functional calculus. A unique continuous functional calculus that's denoted by gamma for A on K. So if we'll look again at this exercise, you see that to construct such an example, we have to take a unital Banach algebra, a unital Banach star algebra, which is not a C-star algebra. And moreover, if K is exactly the spectrum of A, then gamma is an isometric star isomorphism. An isometric star isomorphism of the algebra of continuous functions on the spectrum onto the C-star subalgebra of A generated by A and the identity. That is onto this C-star subalgebra of A. Now, to prove this theorem, let's observe that we may assume from the very beginning that K is exactly the spectrum. In the general case, K contains the spectrum. But we may assume that K is exactly the spectrum of A. Well, indeed, why is it so? If K contains the spectrum of A, then we have the obvious restriction map from C of K to the algebra of continuous functions on the spectrum. Just the restriction map. So if we have already constructed the functional calculus on the spectrum, if we have already constructed such gamma A, then we just can compose gamma A with the restriction map. So let's to avoid confusion, as denoted by gamma A sigma A on the spectrum. So if we compose these two homomorphisms, then what we get is exactly the functional calculus for A on K, just by the definition of the functional calculus. So now our goal is to construct the functional calculus on the spectrum, or more exactly, on the algebra of continuous functions on the spectrum. Okay, so let's consider the C-star subalgebra of A generated by little a and the identity, and that's denoted by B. And we observe that B is a commutative C-star algebra, a commutative unital C-star algebra. So we may apply the Gelfand-Nyberg theorem to B. And before we apply the Gelfand-Nyberg theorem, let's also recall that B is spectrally invariant in A. So the spectrum of our element little a, calculated with respect to A, is the same as the spectrum of A calculated with respect to B by the spectral invariance. This was proved at the previous lecture. That any closed C-star subalgebra, any closed unital C-star subalgebra of any unital C-star algebra is spectrally invariant. So we have this equality. Okay, let's now define the following map, as denoted by phi, from the maximal spectrum of B to the spectrum of A. And phi is just the phi of x is just a hat of x, where A is the Gelfand transform. So, in other words, phi is the co-restriction of a hat to the spectrum. So, by the way, let's recall that the range of the Gelfand transform is exactly sigma of A. This is one of the properties of the Gelfand transform. So we see that phi is surjective. Phi is a continuous surjective map, just by the properties of the Gelfand transform. Let's now prove that phi is injective. Well, indeed, if we have 2 points in the spectrum, x1 and x2, we identify, as usual, we identify the maximal spectrum with the character space, B hat. And suppose that phi of x1 equals phi of x2. So this means that x1 applied to A equals x2 of A. This is just a hat of x1 and this is a hat of x2. So they are the same, but let's now recall that each character is a star character. Each character with C-star algebra is a star character. So they are the same on A star as well. But B is generated by A and the identity. So B, let's look once again here, B is explicitly given by this formula. So it follows from this formula that if x1 and x2 are the same on A and A star, then they are the same everywhere. So this implies that x1 equals x2. So we conclude that phi is bijective. Well, and a continuous bijective map between compact Hausdorff spaces is a homeomorphism. Phi is a homeomorphism. Okay, and now we are ready to construct the functional calculus. So we take the algebra of continuous functions on the spectrum, and by using phi, we see that we have an isometric star isomorphism, phi dot, onto the algebra of continuous functions on the maximal spectrum of B. So phi is a homomorphism, and so it induces an isometric star isomorphism between these algebras. Well, this algebra is isomorphic to B by means of the Gelfand transform. So this is the inverse. This map, this arrow is the inverse of the Gelfand transform of B. And B is a subalgebra of A. And now we define gamma to be the composition of these maps. So by construction, if we look at this picture, then we see that gamma is indeed a unital continuous unital star homomorphism, and it is, moreover, it is an isometric star isomorphism of this algebra onto B, because these two errors are isometric star isomorphisms. So now to complete the proof, we have to show that gamma satisfies our definition. So that is, it takes little t, the enclosure map, little t to little a. That is, what we want to prove is this equality. Well, let's write down this explicitly. So gamma is gamma B inverse applied to phi dot of t. So this should be equal to little a. Okay, let's now apply big gamma to this equation. So this is equivalent to phi dot of t equals gamma A. Gamma A is just a hat. And phi dot of t, by definition of phi dot, this is the composition of t and phi. But this is obviously true, because phi is just, where's phi? Phi is just the Eagle-Font transform, the co-restriction of the Eagle-Font transform. So phi composed with the inclusion map of sigma into the complex plane is just a hat. So this is true by construction. And so gamma takes little t to a. And this completes the proof. Okay, so let's make two simple observations concerning this result. First of all, if f is a polynomial in one variable, well, each polynomial can be considered as a map from the complex plane to itself. So we may restrict f to k. This will be a continuous function, and then apply gamma. So we observe that this is nothing but f of a. Well, obviously this is true because gamma takes t to a. So it takes any polynomial f to f of a just because it is a unital homomorphism. And more generally, suppose now that f is a polynomial in two variables, x and y. And we define a function as denoted by f tilde from the complex plane to itself by the following formula. We substitute z and z bar, the complex conjugate, into f. So it is, of course, this is a continuous function on the complex plane, and we can restrict it to k and substitute into gamma. And again, because gamma is a unital star homomorphism, we see that this is nothing but f applied to a and a star. Just because gamma takes t to a, and it's a unital star homomorphism. So briefly, we can write this as f tilde of a. Well, and these observations justify the following standard notation. For each continuous function f on the spectrum of A, we denote by f of A the element gamma of f. So this is reasonable because in the case where f is a polynomial or a polynomial in two variables, we get just f of a in the usual sense. So we keep the same notation for any continuous function on the spectrum. Let's now look at some basic properties of the functional calculus. The first basic property is the so-called spectral mapping theorem. Spectral mapping theorem. So as before, we suppose that A is a unital C-star algebra, little a is a normal element. Normal element way. Then, for any continuous function f on the spectrum of A, we have the following elegant and easy to remember formula. The spectrum of f of A is the range of f on the spectrum of A, the image of the spectrum under f. So in the previous term, we proved this formula for polynomials. And now we see that if A is a unital C-star algebra and little a is normal, then the same formula holds for any continuous function on the spectrum. To prove this result, we look at the left-hand side of this equality. Sigma of f of A, what is this? First of all, f of A is gamma of f, just by our definition. This is gamma of f. And let's now replace A by B, by the C-star subalgebra generated by little a and 1. And by the spectral invariance, the spectrum will be the same. Where B as before. But gamma is an isomorphism of the algebra of continuous functions on the spectrum onto B. So since it is an isomorphism, we see that this is nothing but the spectrum of f, considered as an element of the algebra of continuous functions on the spectrum. But this is just the range of f. The spectrum of a continuous function is its range. And that's it. We say that sigma of f of A is equal to f of sigma of A. Another useful property of the functional calculus is the so-called superposition property. Again, we suppose that A is a unital C-star algebra, little a is a normal element of A. Also suppose that f is a continuous function from the spectrum, is a continuous function on the spectrum of A, and G is a continuous function on the spectrum of f of A. Then I claim that G applied to f of A is nothing but the composition of G and f applied to A. Well, this is not, this formula is not tautological because, well, the left-hand side is the iteration of two functional calculi. First we apply f to a, and we use the functional calculus for a, and then we apply g, and this means that we use the functional calculus for f of a. And here we first compose g and f, and use the functional calculus for a. And by the way, let's observe that the right-hand side is well defined by the spectral mapping formula, because the domain of G, sigma of f of a, the domain of G is equal to the range of f, to f of sigma of a. So we can compose G and f because of the spectral mapping theorem. So this is well defined. The proof is rather easy. To prove this result, we consider map, that's denoted just by gamma, from this algebra, continuous functions on the spectrum of f of a to a, given by the following formula. Well, gamma is obviously a composition of two unital star homomorphisms. The first one is the homomorphism which takes G to G composed with f, and the second one is the functional calculus. So gamma is a unital star homomorphism. Gamma is a continuous unital star homomorphism. And it takes a little t to t composed with f applied to a. But t is the inclusion map, so this is just f of a. And if we now recall the definition of the functional calculus, we see that gamma is nothing but the functional calculus for the element f of a, because it is a continuous unital star homomorphism which takes t to f of a. So it is the functional calculus for f of a, but this is equivalent to our formula. And this completes the proof. Well, okay, a little problem with the functional calculus. That in the general case, this functional calculus is not given by an explicit formula. And it's easy to understand why it is so. The construction for gamma involves the inverse map of the Gelfand transform, which is quite unexplicit. So we know that the Gelfand transform is an isomorphism, but we have no explicit formula for the inverse map. And that is the reason why gamma, in general, gamma is not given by an explicit formula. However, there are many important cases where the explicit formula exists. Let's look at two examples, or rather two simple exercises. Example exercise 1. Suppose that A is the algebra of continuous functions on a compact Hausdorff topological space, X. And, well, X is a compact Hausdorff topological space. I claim that for each element A in our algebra, and for each continuous function f on the spectrum, the element f of A is just f composed with A. So A is a continuous function on the spectrum, f is a continuous, A is a continuous function on X, f is a continuous function on the spectrum, that is on the range of A. We just compose f and A. This is more or less immediate from the definition. And a little bit more interesting example. Example exercise 2. It is quite important because we will see soon that this example actually describes the functional calculus for any normal operator on an arbitrary Hilbert space. So we suppose now that, let's denote by H. First of all, suppose that we have a measure space, omega mu. Suppose it is a sigma finite measure space. And suppose that f is denoted by phi. Suppose that phi is an essentially bounded measurable function from omega. And let's consider the multiplication operator m phi, which acts on the big O2 space. This is just the pointwise multiplication by phi. Well, the algebra of bounded operators on L2 is a C-star algebra, and this is easily seen to be a normal operator. The adjoint operator is the multiplication by the complex conjugate function. So this is a normal operator, and so we have a functional calculus. So I claim that this functional calculus is given by the following formula. For every continuous function f on the spectrum of this operator, the operator f of m phi, is again the multiplication operator by the following function, f composed with phi. In particular, to prove this formula, first of all, we have to give a meaning to this expression, f composed with phi, because in general, phi, well, the spectrum of m phi is not the range of phi, but it is the essential range of phi, which is different from the range. And so, first of all, we have to explain how we compose f and phi. Well, this can be done in a rather rigorous way, and this formula is indeed true. Okay. Okay. Now we eventually came to the culmination of our course, namely to the spectral theorem for bounded self-adjoint operators on the Hilbert space. In fact, the spectral theorem is not a theorem in the usual sense of the word. It is rather a collection of results, a collection of theorems, which give us some useful information about the structure of a normal operator, and which are very closely related to each other. And in fact, some people say that different forms of the spectral theorem are equivalent to each other. Well, in my view, this is not exactly the case. The process of deducing one form of the spectral theorem from another one is sometimes it is not always immediate, and it is not automatic. So, in summary, we have several forms of the spectral theorem. All of them are very useful because they describe the structure of an arbitrary normal operator. So they are very useful, and they are closely related to each other, but they are not equivalent, at least formally. And so today, our first goal will be to prove one of the forms of the spectral theorem. Let's call it spectral theorem 1. This is the spectral theorem in terms of functional models of linear operators. Well, first of all, let's start with some motivation. all, let's recall a classical result of linear algebra. Suppose that we have a finite dimensional Hilbert space and a self-adjoint operator. We assume that it is self-adjoint just for simplicity. We could actually take a normal operator, but for convenience, let's suppose that it is self-adjoint. Then there is a classical result of linear algebra that T, our operator T, is diagonalizable in a suitable orthonormal basis. And this result can be equivalently stated as follows. We have a unitary isomorphism between H and Cn. So this isomorphism corresponds to a choice of an orthonormal basis of H, such that our operator, such that this isomorphism is unitary equivalence between T and the diagonal operator, the operator given by a diagonal matrix on Cn. Okay, so this is linear algebra. Let's now recall the Hilbert-Schmidt theorem. So suppose now that H is an arbitrary Hilbert space. For convenience, let's suppose it is separable infinite dimensional Hilbert space. And suppose that T is a compact self-adjoint operator on K. So we call the Hilbert-Schmidt theorem, which essentially states that there is a unitary isomorphism between H and the little L2 space, which is a unitary equivalence between T and the diagonal operator M lambda. So M lambda is the diagonal operator, which just the pointwise multiplication by lambda. So essentially, this is the Hilbert-Schmidt theorem for the separable case. So now what we're going to do is to prove a version of these results for arbitrary self-adjoint operators. So now suppose that H is any Hilbert space, and T is a self-adjoint, a bounded self-adjoint operator on H. What we're going to do is to show that there exists a measure of space, omega mu, and a unitary isomorphism between H and L2 of omega, such that this isomorphism, this unitary isomorphism, is actually a unitary equivalence between our operator T and the multiplication operator on L2, the multiplication operator by a suitable bounded measurable function phi on omega. Bounded measurable function on omega. So this is one of the forms of the spectral theorem, more exactly the spectral theorem in terms of functional models. So this diagram, briefly this diagram, says that each bounded self-adjoint operator has a functional model. So this is the functional model of our operator. So in the special case where T is compact, we see that this is also a functional model. This is just a special case of the functional model. In this case, omega is just the natural numbers, mu is the counting measure, and the multiplication operator is the diagonal operator. And in the finite dimensional case, omega is a finite set So L2 of omega is just Cn, and the multiplication operator is just the usual diagonal operator on Cn. In fact, it's a rather easy and useful exercise to show that indeed the spectral theorem in terms of functional modules implies the Hilbert-Schmidt theorem. We'll not do it explicitly, but this is a useful exercise. That is, if T is of this form, and if we assume that H is separable and T is compact, then actually the big L2 space reduces to the little L2 space, and the multiplication operator reduces to the diagonal operator. Okay, so this is our goal. Before we prove this result, let's recall some basic facts from measure theory. Well, actually, we have already discussed these facts in the previous term, but they will be quite essential for the spectral theorem, so let's now recall some of them. So suppose that we have a set, X is a set, A is a sigma algebra of subsets of X, and suppose that mu is a sigma additive complex measure. A sigma additive complex valued measure on A. So I'd like to stress that mu is complex valued, and mu is not allowed to be infinite on any set. So it is always finite, just by assumption. Then we recall the definition of the variation of mu. We define the variation of mu to be a function denoted like this. This is a function of the same sigma algebra. It is non-negative, and a priori it can be infinite sometimes, and it is given by the following formula. For any measurable set A, we consider all finite partitions of A into disjoint pieces. For each such partition, we consider the sum of the absolute values of the measures of the respective sets. And we take the supremum over all such partitions. Of course, if mu is non-negative, then this is just mu of A. If mu is non-negative, then the variation of mu is just mu. But in the general case, this is different because this is always non-negative. The variation is always non-negative. So in fact, this definition can be given for any finitely additive measure. And in this case, mu, indeed, the variation of mu can be infinite. But in fact, since we have assumed that mu is sigma additive, it turns out that the variation is always finite. This is a fact. So the variation of mu is always finite. And it is also a sigma additive measure. A sigma additive measure of Okay, let's now suppose that X is not just a set, but X is a compact Hausdorff topological space. And we suppose that A is not just an arbitrary sigma algebra, but A is the algebra of Borel subsets of X, the Borel sigma algebra. That is the smallest sigma algebra containing open sets. And we recall the following definition. If I have a complex measure, a complex sigma additive measure, mu the Borel sigma algebra. Then we see that mu is a Radon measure. A Radon measure, or a regular measure. If it is compatible with the topology in the following sense: for each Borel subset B of X, and for every positive epsilon, we can find a compact subset K of B and an open subset U containing B. So K is contained in B and U contains B, such that the variation of mu of U minus K is less than epsilon. So roughly this means that each Borel set can be approximated by compact sets from inside and by open sets from outside. So this is B, this is K, and this is U. Then, in some sense, U minus K is small. Its measure, its variation is small. We will use the following simple property of Radon measures, a proposition. Suppose that X is a compact Hausdorff topological space. Mu is a positive Radon measure of X. As before, we assume that it is finite, a finite positive Radon measure on X. Then we can consider the following map, the map from the algebra of continuous functions on X to LP of X mu, which takes each continuous function to, well, more or less to itself, or more precisely to the equivalence class, the mu equivalence class of F. So I claim that this map has dense image. For each p between 1 and infinity. But of course, p should be finite. If we consider the map from C of x to L infinity, then it is not. Its image is not dense. But for finite p, this map has dense image. The proof is a simple exercise for you. Actually, this is a simple combination of Poisson's lemma with the definition of a Radon measure. So, since mu is a Radon measure, it's easy to see that it suffices to show that characteristic functions of compact sets belong to the closure of the image. And this fact can easily be deduced from Poisson's lemma. Okay, now for each compact Hausdorff space X, we denote by M of X the space of all complex Radon measures on X. This is easily seen to be a vector space under pointwise operations, and actually it is a Banach space. M of x is a Banach space with respect to the following norm. The norm of a measure is the variation of mu applied to x. And we have the following fundamental result, which is usually referred to as the Rees-Markov-Kakutani theorem. So this result states that we have an isometric isomorphism between m of x and the dual of c of x. More exactly, the map from m of x to the dual of c of x, which takes each complex Raban measure mu to the integral with respect to this measure. This map is an isometric isomorphism. So this is a classical result in measure theory, and we will use it several times in our approach to the spectral theorem. Okay, so these are some facts from measure theory. Before we prove the functional modal theorem, spectral theorem in terms of functional modals, let's discuss some pure algebraic notions. Well, not purely, some algebraic notions, but of course related to functional analysis. In fact, what we're going to do is to prove a more general result about representations of commutative C-star algebras. And then we deduce the spectral theorem as a special case of this algebraic result. So to formulate our result, we need some notions related to star representations and star modules. Star representations and star modules. So suppose that A is a Banach star algebra. By definition, a star representation of A on the Hilbert space H is a star homomorphism. Pi from A to B of H to the algebra of bounded operators on H. And since we are interested mostly in unital, in Banach algebras, let's adopt the following convention that A is unital and pi is also unital, that is, it takes the identity of A to the identity operator on H. And let's also recall that if you have a star representation of A, then it is automatically bounded, and its norm is less than or equal to 1. Pi is bounded, and the norm of pi is less than or equal to 1. This was proved at the previous lecture. In fact, I proved that any star homomorphism from a Banach star algebra to a C-star algebra satisfies this condition. But B of H is, of course, a C-star algebra. B of H is a C-star algebra, so pi is automatically bounded, and its norm is less than or equal to 1. And let's now introduce the notion of a star module, which is in fact equivalent to the notion of a star representation, but which is sometimes more convenient. So by definition, a star module over A is a Hilbert space H together with the structure of a left A module. With a with a left A module structure. Such that the following reasonable conditions hold. First of all, the action of A on H is continuous. The action of A on H is continuous. And second, the involution on A is compatible with the inner product on H in the following sense. The inner product of AV and W is equal to the inner product of V and A star W. For all A in our algebra and for all V and W in our space. And also we adopt the convention that the identity of the algebra acts by the identity map. You can now compare this definition with the definition of a star representation. We can easily observe that they are equivalent. Or more exactly, we have a one-to-one correspondence between star representations of A and star modules over A. We have a bijective correspondence between star representations and star modules. More exactly, once we have a star module, H over A, we can construct a star representation pi of A on H as follows. For each A, we define pi of A to be the operator which takes V to AV. So this AV comes from the module structure. And this pi is easily seen to be a star representation. So property 1 implies that pi takes A to B of H to the algebra of bounded operators. This follows from property 1. And the fact that pi is a star homomorphism follows from property 2. And the other way around, if we have a star representation pi, and if we read this formula from right to left, we see that this formula determines a star module structure on H. And again, for example, axiom 2 follows from the assumption that pi is a star homomorphism. So star representations and star modules are just two equivalent languages for the same, for essentially the same set of objects. And let's also observe that if we have a star module, if H is a star module over A, then we have the following inequality. For all A in our algebra and for each V in H. Why is it so? Well, this is equivalent to the fact that the norm of any star representation is less than or equal to 1. Okay, let's now introduce star morphisms between star modules. Here we have two star modules, H1 and H2, star modules over A. Then a star morphism, or just a morphism, phi from H1 to H2 is a bounded linear operator, which is an A-module morphism. That is, it has the property that phi of AV is A phi of V. So simply this is a bounded A-module homomorphism. And by unitary isomorphism between star modules, by unitary isomorphism we mean a star morphism which is a unitary operator. That is, it is bijective and preserves the inner product. And we say that H1 and H2 are unitarily isomorphic. And we will use the following notation. If there is a unitary isomorphism between H1 and H2. Okay, let's now look at, before we look at examples, we introduce an important special case of star modules. We introduce the notion of a cyclic star module. So suppose that H is a star module over A, and V is an element in H. We define the cyclic submodule of H generated by V to be the following module. We denote it by AV bar, and by definition this is just the closure of the set of all elements AV where A runs over A. So clearly this is the smallest closed submodule of H containing V. The smallest closed submodule containing V. We say that H is cyclic. We say that H itself is cyclic if there is a vector V. H is cyclic if there exists an element V in H such that the cyclic submodule generated by V is equal to H. And each such vector V is called a cyclic vector. A cyclic vector of H. Of course, it is not unique in the general case. There can be many different cyclic vectors for the same module. Let's now look at some examples of star modules. In fact, our examples will be typical. Example 1 is a typical example of a cyclic module. Suppose that X is a compact Hausdorff topological space. And mu is a positive radon measure. A positive radon measure on X. Let's consider the big L2 space, L2 of X mu. And let's observe that it is a cyclic star module. A cyclic star module over C of X, over the algebra of continuous functions on X. Well, the action of the algebra on L2 is just the pointwise multiplication. The action is just the pointwise multiplication. And why is it cyclic? Well, let's consider just the function which is identically 1. Of course, it is an element in L2 because the matter is finite. And I claim that this is a cyclic vector. Well, why is it so? Well, this is actually equivalent to the fact that the canonical image of C of X in L2 of X is dense. When we act by A on the function which is identically 1, and if A runs over C of X, what we get is the canonical image of C of X in L2. And after we take the closure, so we get now L2, because the canonical image of C of X is dense in L2. So it is a cyclic vector, and so this is a cyclic, L2 of X is a cyclic star module. And we will see soon that this example is typical in the sense that each cyclic star module over C of X is of this form. This will be our preliminary version of the functional model. And example 2, and this example is also typical. Suppose now that we have a sigma finite, well, not necessarily a sigma finite, an arbitrary measure space. Measure space. So mu is not necessarily finite and is not necessarily sigma finite. An arbitrary measure space. And first of all, observe that L2 of omega mu is a star module over the algebra L infinity of bounded, essentially bounded measurable functions. Again, for the pointwise action. The action is the pointwise multiplication. And now let's suppose that we have a compact Hausdorff topological space, X. A compact Hausdorff topological space, and a measurable map, phi, from omega to X. When I say measurable, I mean that it is measurable with respect to the Borel sigma algebra. That is, the preimage of every Borel set is measurable. Measurable map. Then phi induces a star homomorphism, phi dot, from the algebra of continuous functions on X to L infinity of omega. By the usual formula, it takes f to f composed with phi. So if f is a continuous function, then it is bounded, and after we compose it with phi, we get a bounded measurable function on omega. So phi dot is a star homomorphism. Phi dot is the unit of star homomorphism. And by using this phi dot, we can make L2 into a star module over C of X. L2 of omega mu becomes a star module over C of X. More precisely, the action of our algebra on L2 is given by the following formula. Well, let it be better G. So if G is a function in the little L2 space, in the big L2 space, and f is a continuous function on X, then we apply phi dot to f, and this will be a bounded measurable function on omega, and then take the pointwise product with G. So L2 becomes a star module over C of X, and we will use the following special notation for this module. So this is the L2 space considered as a star module over C of X, where the module structure is determined by phi. And we will see soon, we will see at the next lecture, that every star module over C of X is of this form. So, in summary, we will see that example 1 describes all cyclic modules over C of X, and example 2 describes all star modules, not necessarily cyclic, all star modules over C of X. And this is our general form of the functional modal theorem. And this is our plan for the next lecture. So at the next lecture we will prove these results, and then we deduce the operator version of the spectral theorem as a special case. Okay, thank you.